So, thank you for the invitation, and I try to speak slowly, so maybe you can understand my English. My mother language is German, so also my English is not perfect, but it's more easy to understand than perfect English. Okay. So, I have similar age as Morimoto, and my basic education is physician, but I also worked in hospital, but most of my career I worked with the Federal Institute of Technology, and so that is teaching to engineers about human factors and ergonomics. And human factors has several sides. So one is to produce faster, to produce more, to make use of the human body as good as possible. And the other side we could also call health ergonomics, or health human factors, how to design a workplace that people stay healthy. And I'm a physician, so actually I try to combine occupational medicine and ergonomics. But the Federal Institute of Technology doesn't think that this field of research is very important. So now I'm a part of this lab, Sensory Motor Systems Lab, that is directed by Professor Robert Wiener, and it's about robotics and rehabilitation. I do have a second job with the Swiss government, and about this job and what I do, I will talk with the next talk. So, Morimoto invited me to give a presentation. So this presentation is mainly what is the research that is directed by Professor Robert Wiener. The second will be what I do with the Swiss government. And the third is just one example of many research projects I'm leading. So here we work. I will show a short movie where you can see more, so that's the outside. So if the weather is nice, we have quite a spectacular view, and there's also a restaurant here, so it's nice to be there. I cannot present all research that is done at the Sensory Motor Systems Lab. So I will talk about this example called Locomart, and that's rehabilitation of maybe after spinal cord injury or after stroke, and subjects should learn to move their legs. So I will present some points about this machine. This is also commercially a successful machine. And the second, this will be a bit shorter, is the same but for arm rehabilitation. And you will see that it's really a robot. It's a robot because partly it senses what the people do and react on what the patients do. So it's not just a machine, it's really a robot. As I've already said, my presentation is based on slides from two presentations that were given by the director, Robert Wiener, and then I show a movie that is done by Josias Kuppo. So, why would we construct such an expensive machine, and why would hospitals really buy it? So that is because rehabilitation of legs, this is a demanding work. For the therapist, it's quite exhausting. And you know, you have a back like that or so you can't do it for a long period. And that means for the patient, he has not so many hours training per day as he should have. And also it's very difficult to really make optimal training because it's so hard just to do the training. So if it's possible to have a robot helping, this is really something that is important and helpful. And now, this is now the commercial product. Afterwards, we will see the research product. And there are more than 200 publications now about this system. And most of all show positive results. But the advantage compared to conventional therapy is very small. So it helps, but we think it should do much better. And so our research is, why is the advantage so small? Of course, it's a huge advantage because a patient can do it by himself. We don't need staff and things like that. So it's very clear that it's useful. But we would expect that we'll have better results. And what can be improved? We need enough machines so that training is long enough. Training should be intensive enough. Training should be fun. We learn from errors. We benefit from social support. And training should be relevant for real life situations. So this is very basic knowledge in learning science, but it's not so basic for robot scientists. So the task is to bring now all the knowledge about learning to the mechanical engineers and to combine it. And I think Robert Riener does it very successfully. So now this is now the circle. We have the human, we have sensors of the machine, we have the interaction. The machine can communicate with loudspeakers, with screen, but also with vibration and things like that. Okay. We have a focus of exoskeletons for clinical rehabilitation and Locomat and arming, and now we are going into the direction of portable exoskeletons, but this is for daily life. If we look at therapy, actually it doesn't matter if it's a very complicated machine or portable. This is not relevant because we want just to have rehabilitation and learning. But if we want to help in daily life, of course, it should be portable and we should, yes, okay. So we should think about learning, and we do a lot of experiments about learning. And if we think about stroke patients, also different area of the brain may be damaged. So maybe in the future we think, oh, this part of the brain is damaged, we should concentrate the therapy on this part. So it would be very good if we know which part of the brain is activated by which therapy. And this is just a very recent slide, so it's only an example. It's not that we really have to prove that it is correlated, but we have huge differences in the activity in the brain in this patient, depending on what kind of feedback the robot gives. So the task was just to move the legs, and of course it was hard to build such a machine that is compatible with functional magnetic resonance imaging. So this was just one PhD work, was just to construct this machine. And now this is now the first measurements, and the machine gives feedback how good do you learn to move your legs? And the feedback is changed, so it's not just just one-to-one feedback, it's a changed feedback. So here the feedback is not precise, it's noisy. And here the feedback shows bigger errors than the real errors, because this is based on learning theory that with this kind of feedback maybe learning can be improved.
How long?
Oh, this wasn't so long.
So long.
Maybe a few minutes. I think 20 cycles or something. Yes. You know, this is really development of technology. This is, yes, maybe 10 years that it's really in practice or even more. But I show it here because it shows that really learning is relevant, and it's not just a kind of psychological problem, it's also a morphological problem. So we can learn, even if we are old, we can learn. Our brain with less neuroplasticity. And from learning therapy we know that high intensity, own activity, social interaction, we learn better. And that's the same if we would like to learn a language. So if you learn English, please do it intensively. Do it yourself, be active, and do it together with other people. Then you will have success. And if you have a paralytic leg, the same is true. So, but how to integrate now social interaction with a robot training? You will see it's possible. And then we also must be aware of the sensory motor characteristics. We know that we have just a controlled movement. We can do it again and again and again. Learning is nearly zero. But if we have a movement and the robot is only helping, then this is really helpful. So, for instance, think about the paraplegic arm, and I can't move, and I try, and now you see just a little movement. But if the robot is holding the arm, and actually that was the start of this development, that actually it wasn't a robot, it was just a machine, that the weight of the arm is zero, then you make this very small muscle twitch, and you have a movement. And then you feel the movement, and then your brain can learn. But if your arm is so heavy that you can't move, then maybe you do the right thing, but you have no effect and you don't learn, or only very little. So this was the start. And this is, there's a lot of literature that really shows it, that passive training isn't good. And also that if the feedback is very fast, if it's too often, then actually fast is okay, but very, very often, very frequent is bad. And the passive behavior is not good. And also with the locomotor, if it's fully, a locomotor just moves your leg and you do nothing, actually you may learn that the machine moves your leg and you forget to be active yourself. Also in the lecture, if you don't think yourself, but just follow what we are presenting, but not think about it at the same time, you learn very little. Of course, you can follow during the lecture without much thinking, but afterwards at home, you must look at it and have your own ideas. This is about learning. Okay, so this must also be done in therapy. And it's also better to really learn a skill and not just the movement. So I want to have a cup of coffee. I want to reach there and not train movement. That is helpful. And this assist as needed, this was also shown in animals, so this is really basic principle. Okay. And here we have also some first examples that if we have help as needed, then success is better. Okay, so this is actually what we continuously try to integrate into the quality of the robot. So now the robot behaves assistive. He gives a correction or is really transparent, so we understand the robot, and it's only when it's needed, and that is allows free timing for the patient. We support the patient, but do not restrict the patient. So for instance, now, if you have a movement pattern, we know this is optimal. And then maybe outside here, it's so much outside, it's not helpful anymore. Maybe it's not dangerous because the subjects are well supported, but it's far away of what we want to learn, so we still have some restriction. But in here we have just a field that it's maybe you have, the more you deviate, the more you have a force against it. Here we can have a lot of different kind of software. We can wait a long time, a short time. So this still, there's a lot that can be improved. And this is now from a technical point of view. We have here some elastic control, and here clearly then in the end a strict bound. And now this leads, this is now like if we have position control, then we know the position where the leg would be, and we do not allow deviation. Then repetition is always the same, and we know now from learning experiments that this kind of repetition is not good to learn anything. If we have path control, each repetition is slightly different, so this is human behavior, and this is better for... Knee angle, aha, okay, yes. This is a Liachu diagram, and it just gives the angle at the hip and the angle at the knee. So if we have completely like always the same, and if we move, you know, we always move the hip and the knee. And then we can show it simultaneously. So yes, so this is illustration of hip and, you know, but I didn't go into detail because we could also use foot angle, any part of the body. It just demonstrates, yes. So any part of the body will have identical movement with position control, and with path control we allow for variation. Because you try, and if you deviate too much, you get feedback or help, depends on how good you are, and then you try again and again, and or maybe the human error is always at a different point, and we learn from errors. So now this is quite new that it really works. So we did a few patients, so we also work together with an orthopedic clinic. Actually, they have a big center for rehabilitation. And you might have seen on the first slide that Professor Läubli is also has a professorship at the medical university. And so this was now locomotor gait training 7 months after stroke. So kind of stabilized, but still with now training with the path controllers, and he showed, we give now here also with the same, the ankle against the hip, so he can follow what he's doing, and he can try his best. He has, so now he has also a visual feedback, how he's behaving. And it seems that now improvements are really better, that it's larger. It was larger compared to therapist assisted, and it was also, and this was also seen again. But now this is now we go to larger randomized clinical trial. So you know, I actually now I talk about ongoing research and not about clear results. Okay, so path control, we are sure it supports learning. Okay, then something else is motivation. You know, if you are bored, then even if you practice, it's, what you learn is not really fixed in your brain. You will lose it. So also, the same is also done with children after accidents, also with brain damage. And in children, it's even more important to have that they like the training. Okay, so we do animation. And now you see again the simulate that we have here we have the human, and we have the robot, that we have some auto vision, and now the robot measures also the reaction. And now it's nice if we adapt the scenery, so also the scenery should move faster if the human moves faster. But it's a robot, so that it's not that sometimes here it's slower and then the picture is slow and then here it's faster. No, the patient now walks faster and it's noticed, and then the picture also is faster. And then also to increase arousal is important, that here really the whole brain is active. Okay. So now if we go the system more into detail, then we need Kalman filtering, we need discriminant analysis, we need a state estimator to really to know what is needed. So we do a lot of research on this psycho-physiological control loop. We use ECG, skin temperature, then breathing, and whatever is possible, and try if it's helpful or not. Yes, so this was the first part. Afterwards I will go a bit to the arm and then to cytoplasm, but before I want to show you our lab. So that's really, so we have similar color as you, and that's the student room, but Robert Wiener asked that it must be in good order, so it's different to keep. This is Robert Wiener in his office. So this is a rowing robot, and here we study learning, so I will not present the data here. So this is arm training. This is one of the PhD. So actually he's done his PhD. Now it stays a bit longer. And this is now first steps in building an exoskeleton. We mainly build it to exactly measure the locomotion. Yes, that's our real coffee machine. Now a little about biomechanics and manufacturing. Of course, we would like that the exoskeleton would do the same movement as the robot, as the human, but we must fix it somewhere, and then it doesn't really fit. So if you so it will move up and down here, you have some friction, and of course this is not nice, especially if you learn a new movement and instead of a very nice proprioception of what you learn, you rather learn how the robot reacts. So we need to avoid that. So also mechanical engineering is quite important. And here they did a lot of work and also have a patent to have a robot that really is also exoskeleton the technique, and you see it's complicated. So this is now with the arm. The same system what we're developing now is for the hip, that you really can do natural movement with the hip movement, and not that you're fixed and only in leg movements. And we can change from the left side to the right side, and we can really adapt. Okay, and if we have path control and a good fit of exoskeleton, then it's possible to really do natural movements. And if we don't have this, actually it's not possible. That's why also these machines are a bit expensive. Now, what we do now, and just now a clinical trial is going on, that we have two arm robots and we have a game, and so you can play a computer game together. And actually we also made then games that are competitive or games that are collaborative. And we did the psychological tests, and really some people like more the one and the others more the other, and we can give what they want. Yes, and this seems to be really beneficial. So you see, even if we have robots, such big machines, we can we do it like that. Actually, Masaru and me, I think we were patient couple 3 to do the training with this machine. Yes. And then also we should train useful tasks. So virtual reality is tasks that you need, but because you need to do so much training, you should also train what you like. It's necessary that the training is some fun. Okay, so this leads to conclusion of this part. Neuroplasticity asks that we have high intensity in training. We need participation, so that it's important that the robot doesn't do too much. And then we need the flexibility. We really need to avoid repetition. We need a full range of motion, and we need very good fit, so we do not have joint stress. It must be adaptable to many body sizes, and also then with all the software actually also to the mood of the patient. And the motivation is needed, so we must do our best to provide motivation. And we should train activities of daily living and perform real daily life tasks. And you have seen with these examples, in principle it's achievable, but of course then to really have machines that can produce and sell all over the world and that are easy to use, this is a demanding task. So I present here the research part. Okay, so Robert Riener is a successful director, so that means we have many collaboration with other universities, with research center in Switzerland, with university clinic, and this is Procoma is the company that sells this equipment. And then we also have all these sponsors like the Swiss National Foundation and the European research projects. Okay, would you like to have some questions about that, or should I continue and in the end? Has anybody a question? It's not that long. Okay, you want to know about cybercode. So maybe, I think it was 18 months ago or so, then this was just kind of an idea of Professor Robert Riener, but normally these ideas will become reality sooner or later. And then together with his son, he made a movie about his idea, put it on YouTube. And then this was discovered by CNN, and they made an interview with him. And then it was news on CNN, and then he had worldwide reactions, and then since then he's very, very busy. Okay. So actually first we wanted to call it Cyber Olympics, but the Olympic Committee don't want that this kind of sport is considered Olympic. Yes, I think also car race, you know, is not part of Olympic Games. So But I think sports with these powered devices is possible. So, for instance, this famous lady made a marathon. Of course, the class is 16 days, but she did it. Or with a powered prosthetic limb, climbing 2,000 steps is possible. And maybe a few of you have seen at the start of the football game, and actually this is was developed jointly with Brazilian researchers at the Federal Institute of Technology, but mostly in Lausanne. So the professors that developed this also collaborate. And now, wow, what is the cyberclone? It's a championship for pilots. That is the patients with disabilities and paraplegics. And the pilots are allowed to use most advanced robotic devices. And the big advantage is that now really severely affected pilots can participate in such games. I think that's really a good advantage. And then to do it, we need technology. This can come from companies or research labs. And like in car racing, then it's kind of teamwork. The pilot really, he must do it, but also he is in need of technology. So yes, we can't separate. And the outline is clear. Final decision will be this summer. At the moment, and probably it will stay so, it's 6 different disciplines with different technologies. And overall, the tasks should be useful for daily life activities of such a pilot. And actually, a lot of assisting technology is allowed, but a power line is not allowed. So the battery or whatever it is must be taken, the pilot must carry. And the goals is the development of useful assistive systems, and also if we have such games, it removes barriers between the public and users and developers. And now, this is the disciplines. So, powered leg prosthesis, and here you see the circuit. So we think there are slopes, stairs, then you sit on a chair, you have gravels, and then here a teeter toot, a bar, and then some difficult place, slalom, and then here maybe a short, like a small creek, or you must jump over, things like that. This is now the outline, and the definition is this. And then maybe if you need a full exoskeleton, then the circuit is very similar, but of course that's something different if you really need a powered exoskeleton. But then we also will allow for powered wheelchairs. This is not allowed at the Paralympics. So actually that was kind of the start of the idea, why shouldn't we allow that? Because many patients need it. And you know, you can also electrically stimulate the muscles with functional electrical stimulation. And this is with many young paraplegic this is done because they need the movement, they need sport for their heart, for health. So they need this kind of training. So it's more kind of health training, not really to move around. So this is that kind of like a classical circuit, you must be as fast as possible. So this is not meant for daily life, this is for physical fitness. And then with our prosthesis, of course, it's not about walking, it's about using the arm. So the idea is that you must do different things on the table, grasp the grass, things like that. And then also there's actually lots going on with brain-computer interface, so that you really must activate your brain and you have the electrodes, and then you learn to manipulate the brain activities so you can use it to guide something. So that should also be part. Okay. Now the executive board and consultants, it's here. We have always somebody from our institute because the first cyberclub in Zurich. And but also there's now international collaboration. We have an advisory board, and you see it's physician, it's people from industry, it's a Nobel Prize winner that lives in Zurich, actually Winterthur, and also banking major of Zurich. So now we have good support, and this is at the moment that supporting agencies, and it's highly visible, and yes, so we are sure it will happen. Okay, thanks for your attention.